Hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Rosen, the online editor for BioProcess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We have muted the audio lines, but we welcome you to type in your questions for our speaker in the chat window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions from the chat window. Your questions in the chat window will only be visible to myself and our speaker. So thank you for joining us today. It is now my pleasure to introduce our speaker, Mike Johnson from Entegris Life Sciences.
Thank you, Leah, and welcome everyone to this webinar on advanced materials for single-use systems. I'm Mike Johnson, the Market Development Manager here at Entegris. Let's get started. According to Eric Langer and his 2015 annual BioProcess report and survey, the utilization of single-use devices is one of the top factors improving biomanufacturing performance. This supports the introduction of new products, new processes, and new technology, all based on single use. So the single-use industry is doing a lot of things right. But the data from the survey also shows there are still factors restricting the use of disposables in biopharm. These factors include bag breakage, concerns around E&L, and material incompatibility with process fluids. How will these factors be eliminated, and where will the innovation come from? According to the survey, new and improved plastics are being requested. Possible material innovations include a homogeneous film where multiple layers, lamination, and adhesives are eliminated. These innovations can make single-use even more cost-effective. Langer goes on to state that fluoropolymers appear to be very promising to achieve these goals. This high-performance polymer family was developed for challenging applications where durability, inertness, purity, and cleanliness are of utmost importance. Fluoropolymers have proven that they possess unmatched chemical inertness, suitable for exposure to just about anything, including strong acids and bases, salt solutions, alcohols, esters, and aldehydes. Fluoropolymers also have an extremely wide operating temperature range. As you can see here, the maximum use temperature for fluoropolymers is up to 260 degrees C. Other polymers are far below this temperature limit. On the opposite end of the spectrum, and more applicable to bioprocessing applications, fluoropolymers are capable of use down to minus 240 degrees C, while other polymers are being pushed to their limits when used in frozen applications. Advanced materials such as fluoropolymers also have an advantage when it comes to extractables and leachables. Typical polymers in single-use bags have multiple sources for detrimental extractables to come from. Contamination sources include oligomers, additives such as antioxidants, plasticizers, and lubricants, as well as adhesives and catalysts. Fluoropolymers, on the other hand, greatly reduce the risk associated with E&L. This is due to the fact that the fluoropolymers do not use any additives, adhesives, or catalysts. This results in a nearly non-existent extractable profile. Consequently, as suggested by Eric Langer, utilizing fluoropolymer materials in single-use systems has distinct advantages in regards to chemical compatibility, extractables, and temperature use. The data contained on the next several slides was generated from tests performed on a new fluoropolymer single-use bag system. The article used to generate the test data is the Aramis single-use bag system. Aramis is comprised of a single layer of gamma-stable fluoropolymer film. So the product contains no additives, it contains no processing agents, nor does it use any type of adhesives. First, let's take a look at the extractables benefit. As can be seen from this table supplied by the BioProcess Institute, Every organization associated in some way with bioprocessing has an effort to address the topic of extractables. The output of these efforts include E&L protocols, guidelines, risk assessments, and test data. All of this work has been based on the current state of polymers and their associated risk of contamination. The data on this graph shows a dramatic reduction in extractables when using a fluoropolymer. This data compares the Aramis film and a typical multi-layer polyethylene bag for extractables using an aggressive reflux extraction process using 100% ethanol. The data shown here shows that the multi-layer polyethylene bag had 144 times greater TOC than did the fluoropolymer film. In similar fashion, the extractable data shown here was generated using an aggressive IPA reflux extraction process. The results with IPA show that the multi-layer polyethylene bag had 60 times greater TOC than did the Aramis bag. This all results in a greater reduction in risk associated with extractables. Next, let's take a look at material durability. The mechanical data in this table shows that fluoropolymer product is as good or better than a multi-layer polyethylene bag. In terms of puncture strength, they're about equal. Tensile strength at break, the fluoropolymer film is 2 to 3 times better. Elongation at break, they're about equal. And haze testing, the Aramis film is 2 to 5 times more clear than a multi-layer PE bag. But when it comes to cold crack testing, the fluoropolymer material far exceeds the polyethylene bags. Cold crack testing is a method for assessing the brittleness of plastic film and sheeting at low temperatures. This method characterizes a finished product of given thickness and texture. These images show the test fixture that is used for cold crack testing. 6 film strips are inserted into the fixture and conditioned to the test temperature. Once stabilized, a weight, which is shown at the top of the fixture, is dropped onto the test strips, and each strip is then evaluated for any type of damage. The image on the left shows the cross-sectional view of a multi-layer polyethylene bag after the testing, and it shows the fracture that took place through the film material. And this typically takes place at temperatures in the -20, -40 type temperature range. On the right-hand side is a view of the fluoropolymer film strip. As you can see, the material did not fracture or break during the testing, even down to temps below 188 degrees C. Taking the cold temperature testing to extremes, I will now show a video showing how various films withstand exposure to liquid nitrogen at -196. So what you're going to see here is a dewar of liquid nitrogen and 3 different film strips that are being tested. This is a multi-layer polyethylene film that was immersed in liquid nitrogen and removed. And you can see how brittle it becomes after that exposure to liquid nitrogen. This next strip is a single layer of polyolefin material. Again, it's immersed into liquid nitrogen for 30 seconds and then removed. At this point, the film is flexed, and you can see how brittle the material is after that cold exposure. The last strip is a sample of the Aramis fluoropolymer film. As with the other samples, it's immersed into the liquid nitrogen and removed. The material itself remains extremely flexible as if it's at room temperature, maintaining all of its mechanical properties. So you can see very clearly the differences between these film materials when exposed to those cold temperatures. While the film testing is a great tool, ultimately a user wants to know how the material works in the actual application. End users often do comparative testing to determine a bag's durability. Common tests performed by end users include multiple freeze-thaw cycles, simulated drops, and inspection for pinholes and leaks. In order to gather application data, an independent test was performed by PDS Labs. In this test, multiple bags were filled to their rated volume with sodium chloride. The filled bags were exposed to test temperatures, including a 2 to 8 degrees C range, a minus 20 degrees C, and a minus 85 degrees C exposure. After a minimum of 8 hours at temperature, the bags were then dropped from various heights. After being dropped, the bags were inspected for failures such as pinholes, rips, or tears. Materials tested including polyethylene, polyolefin, EVA, FEP, and the Aramis fluoropolymer. This table shows the results of the testing. All the bags passed at the 2 to 8 degrees C range. So they passed the temperature cycle and they passed a 6-inch drop test. Moving to the minus 20 degrees C exposure, there were some failures of the polyethylene bag just due to the cycle to minus 20 degrees C and back to room temperature. The bags that did pass the temperature cycle also all passed a 6-inch drop at that minus 20 degrees C. At minus 85 degrees C, both the polyethylene and the EVA bags had failures during the temperature cycle phase, and both of these bag types had 100% failure during a 6-inch drop test. Taking a look at the polyolefin monolayer material, it passed the temperature cycle, it passed a 6-inch drop test, but it had complete failures at a 12-inch drop as well as a 1-meter drop. Next, the FEP bag passed the temperature cycle, it passed a 6-inch and 12-inch drop, but failed at the 1-meter drop. And finally, the Aramis fluoropolymer, it passed all the temperature exposures, even down to minus 85, and it passed a 6-inch drop, the 12-inch drop, and it was the only one to pass a 1-meter drop at a minus 85 degree temperature range. Again, this assures that the product being contained in the bag has less risk due to droppage of the bag. So in summary, fluoropolymers have nearly universal chemical inertness, enabling use in a wide range of applications both upstream and downstream. Their absence of additives, processing agents, and adhesives greatly reduce your process risk, especially in critical bulk drug storage and final fill applications. Finally, their wide temperature operating range and their robustness at cold temperatures provide higher security of frozen drug product, improving process yields. I thank you for listening, and I believe we have a few minutes left for some questions.
Thanks, Mike. And yes, we do have some questions. If you have a question, go ahead and type it in the chat window, and we'll start off. So the first question I have is, what about the use of autoclaving application in terms of temperature resistance of the bag to heat and extractables and leachables?
Sure. Yeah, I mean, autoclaving is an acceptable form of sterilization for this product. You could actually look into dry heat sterilization as well for this product because of its temperature range capabilities. So, it has no problem or no issues being exposed to those temperatures typically used for autoclaving.
Okay. Is this considered a USP class 6 plastic, and is it gas permeable?
This is a USP product. So the Aramis bag, along with the boat fitment, is tested for USP Class 6. And I would say it's a USP Class 6 product. In regards to gas permeation, we have some data in regards to gas permeation similar to the other bags that are out there. So if whoever has that question, certainly if you want to contact me, we can discuss that in more detail.
Okay, yeah, I'll give you the email address.
Okay, thanks. Yeah.
Also, so we know that fluoropolymer is also used as a material for disposable tubing. For this application, what are the advantages of this material providing over silicone? I'm not sure.
So try to address that in right, silicone or thermoplastic elastomers are typically used for tubing in single-use applications. And just so it's clear that this material or this product is not using a fluoropolymer tubing on it. So the end user or whoever's purchasing the product specs out their type of tubing that they would like on the Aramis assembly. But I guess in comparison to, say, silicone, the fluoropolymer is going to be much cleaner from an extractable standpoint than would a silicone material. So hopefully I answered that question to meet your needs.
Okay. And what is the level of gas permeability compared to other films?
So with the fluoropolymer so this assembly, again, as I stated, it's a single homogeneous film. So unlike the multi-layered polyethylene bags, it does not contain a EVOH layer for moisture and gas permeation. So it is going to be about the same for moisture permeation through the material as a multi-layer PE bag, but it is going to be higher when it comes to gas permeation. And so what Entegris has done is we've performed some pH stability studies, taking a look at frozen product in dry ice and looking at pH stability to check for any type of permeation of the CO2. And that'll be some data that we'll be reporting out on probably in the next couple of months. So I guess I would say look forward to that data being presented at possibly another webinar or a conference in the future.
Okay, well, very good. I think we're running out of time. So if we didn't get to your question, we will be passing those along to Mike, and he can follow up directly. So thanks, Mike, and thank you to our audience for joining us.
All right. Thanks, Leah. Appreciate it, and thanks, everyone, for listening in.
Okay, thank you. So the recorded version of this webcast will be made available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with a direct link. We look forward to having you join us at future BioProcess International Ask the Expert webcasts covering many aspects of bioprocessing. We have quite a big lineup coming up, so look for those announcements in your inbox. Thanks again. Bye.